In this video, we will learn the topic of mathematical induction, which is a method used for proving mathematical formulas or statements. There are two key steps in proving something by induction. Let's say we have to prove some formula S works through induction. The first step in doing this is to prove S works for the base case, which is usually 1. The second step involves making an assumption that S works for some number k, and then proving that S also works for k plus 1 based on this assumption. Now let's apply this method to an actual proof. Let's say S represents the sum of the first n positive integers. Now there's a formula to calculate this. The formula says that the sum of the first n positive integers is n times n plus 1 over 2. I've proved why this formula works in another video using a different method, but in this video we're going to prove the same thing but using induction. So the first step in our proof is to prove that S works for the base case, which in this case we're going to set as 1. We know the sum of the first positive integer is just 1, so we need to verify that 1 is equal to S of 1, that S works for our base case. S of 1 is 1 times 2 over 2, which is equal to 1, and thus we have verified that S works for our base case. The second step in our proof by induction relies on making an assumption, and that assumption is that S of k, which equals k times k plus 1 over 2, works. So we're assuming that S of k, which is equal to k times k plus 1 over 2, correctly calculates the sum of the first k positive integers. What we need to prove is that S of k plus 1, which can be written as k plus 1 times k plus 2 over 2, also works. And we're going to use this assumption in order to do so. You'll notice that S of k plus 1 can be written as 1 plus 2 plus 3 plus some terms in the middle plus k plus 1. And this is because S of k plus 1 is just the sum of the first k plus 1 positive integers. Now these terms over here should be familiar to you guys. The sum of the first k integers is simply S of k, and so this statement is equal to S of k plus k plus 1. S of k equals k times k plus 1 over 2. From this step over here, this is where our assumption comes into play, and then to this we just add k plus 1. Now I'm going to skip some of the intermediate algebra steps here because I'm running out of space. But if you guys have any questions about these steps, feel free to ask in the comment section below. So what we have here is k squared plus k plus 2k plus 2 over 2, and this is equal to k squared plus 3k plus 2 over 2. If we factor, we get the sum of the first k plus 1 integers is equal to k plus 1 times k plus 2 all over 2. You'll notice that these two things are the same, and because of this, we know that if S works for some number k, then it also must work for k plus 1. At this point, we have completed both the steps in our process of proving something by induction, but you might be still wondering how this method proves that S works for all numbers in its domain. In the first step, we proved that S works for the base case. In the second step, we showed that if we assume that S works for some number k, then S must also work for the next number, k plus 1. We know that S works for 1, so by that logic, S must work for 2 as well. If it works for 2, then it must work for 3 as well. If it works for 3, it must work for the next number, 4 as well, and so on and so forth. And thus we've proved that S works for all numbers in its domain. Now let's move on to a more challenging problem. For the more complicated problem, we're going to try to prove that 6 to the power n minus 1 is always a multiple of 5 for all integer values of n greater than or equal to 1. You'll notice that in this case, s is more of a statement rather than a formula. The first part in proving this statement is true using induction is to verify that the statement is true for the base case. The base case is 1, and s of 1 is equal to 6 minus 1, which is 5. Since 5 is a multiple of 5, we have verified that s is true for the base case, and this means we can move on to the next step. For the second step, we assume that s of k, which is 6 to the k minus 1, is a multiple of 5. And what we need to prove is that s of k plus 1, which is equal to 6 to the power k plus 1 minus 1, is also a multiple of 5. You'll notice that 6 to the power k plus 1 minus 1 can be written as 6 to the 1 times 6 to the k minus 1. If we think of this 6 to the k term as u, what we have here is 6u minus 1. We can rewrite this as 5u plus u minus 1. If we substitute 6 to the power k back in for u, what we get is 5 times 6 to the power k plus 6 to the power k minus 1. We need to show that this is a multiple of 5. This term will always be a multiple of 5 because 5 is one of its factors, and this term will always be a multiple of 5 as well because of our assumption over here. So what we have here is essentially the sum of two multiples of 5. So if we take two random multiples of 5, let's say we take 5 and 15 and sum them together, we get another multiple of 5, 20. Let's say we take 35 and 40 and sum them together. These are both multiples of 5. You get 75, which is another multiple of 5. You can do as many of these as you need to convince you that the sum of any two multiples of 5 will also be another multiple of 5. And thus, we know that this term over here must be a multiple of 5 as well. And thus we have proved that 6 to the power n minus 1 is always a multiple of 5 for all integer values of n greater than or equal to 1. And we can use the same reasoning as I used in the last problem to justify that this indeed proves that this statement is true. We know that this statement is true for the base case. That's what we did in step 1 here. And in the second statement, we showed that if we can assume that s is true for some number k, then we also know that s must also be true for k plus 1. And thus, if it's true for 1, it must be true for 2. If it's true for 2, it must be true for 3, and so on and so forth. And thus we have proved that this statement is true through mathematical induction.